Welcome to this little screencast. The purpose of this presentation will be to give you some kind of initial introduction to the statistical tools that we often encounter in experimental reports. It will be divided into several short movies, and the first one will be on descriptive statistics. But first of all, the kind of stuff that we would try to get a better grasp at is these type of phenomena that we encounter, for instance, in result sections in experimental reports. So in this particular little excerpt from the eye tracking study by Senju and Zebra, we see that they have measured some effect to be 2.74, and we have a p-value of 0.013, and really that's the kind of thing that we would like to get a better grasp at. What does this all mean? We also often encounter these kind of graphs where, in this case, we can observe that there are two different conditions, an eye contact condition and a no eye contact condition, and we can see that there is some kind of difference in magnitude here, but there are also other pieces of information, like for instance these lines here, that we might not know exactly how to make sense of, and there are little stars here and that kind of thing. So these are kind of some of the basics that we would like to acquire more knowledge about. But let's start from the very basics. So we can divide statistics in two basic types. The first one being descriptive statistics. And descriptive statistics is designating the way in which we can summarize, organize, or describe various properties of a collected sample of data. So when we perform some kind of experiment, we collect some data that is constitute a sample, and we can characterize the observation in that sample in various ways using numbers. For instance, one very common thing would be to average some data, for instance, taken from different participants. So that would give us some kind of mean of their observed behavior, and we might also want to look at variation in these data. So that is another piece of descriptive statistics that we can look at, and in some experiments it's also relevant to look at, for instance, the accuracy and some scores or something like that. And all of this would be examples of data that, or measurements that characterize that particular sample that we have collected. Then we have another type of statistics, what is called inferential statistics, or sometimes inductive statistics. And we apply those statistical tools when we want, from the observations that we have made in our sample, to form some conclusions. So often the reason why we do experiments is that we want to say something more general about a phenomenon. So we want to generalize a set of observations to a greater population, or to say something very general about a phenomenon. So when we start to apply inferential statistics, really what we want to do is to take the observation from our little sample and then do different statistical tests that can tell us something about if these observations we have made are likely to generalize beyond that sample. And in order to do that, we do what is called significance testing, and I'll return to that in the next video. But first of all, we will look at some of the very basic tools that we encounter in descriptive statistics. Yeah, as I mentioned before, descriptive statistics are different kind of ways of quantitatively summarize some properties or characteristics of some sample data, some data we have collected or has been collected in an experiment. And one of the most kind of fundamental ways in which we often summarize data is by looking at means or averages. This is the same. By looking at variation in the data, and one of the most commonly used concepts is the concept of standard deviations and percent and that kind of stuff. And let's just have a quick look at what an example of this kind of descriptive statistics. So here we have a data table taken from the study by Richardson and colleagues where people were handling planks at different lengths. So here we see a little abbreviation for plank length, and we can go in here and then we can see what was the average plank length at the transition point between one hand and two hand, and later on between two hands. And I think this is using a tool. So we see that when planks were presented in ascending order, then we had a transition point with an average plank length of 13.33. So that's one piece of descriptive statistics or numbers that somehow characterized some observations from that sample. Here's another example. This is taken from the Fay et al. Study where he compared sign systems that had evolved in isolated pairs with sign systems evolved by communicative pairs in a reaction time task where people had to press a button as quick as they could to make particular decisions. So here on the x-axis we have response times in milliseconds, and here on the y-axis we have data from round 1 and round 7 from two different conditions, being here the community version and here the isolated pair version. And basically what this little graph tells us is that from round 1 to round 7 it seems that we get signs that are much quicker to identify somehow. So there's a drop here in reaction time. We see that for the isolated pair evolved signs, we don't have the same kind of drop in reaction time. It's kind of stable from round 1 to round 7. We also provided with some accuracy scores here, and we noticed that people tend to become more accurate when they are presented with signs from round 7 than when they were presented with signs from round 1 and so on. So this is again a little graph that summarizes some of the crucial information from that experiment. Again, we see that there are some lines here that we would like to know something about. Let's return to the table. So as before mentioned, this is reflecting the mean plank length, but we also have a number here in parentheses. And if we go down to the legend here, we can see that what is represented here is the standard deviations. So let's have a look at what that could possibly be. So mean and standard deviations are some of the most commonly encountered ways of summarizing observations in an experiment, in a data set. The mean will sometimes be presented simply by the abbreviation M, and standard deviation is abbreviated SD often. And what does these two things reflect? Now let's just pretend that we conduct a little experiment in class where we have participants here. On this x-axis we have 20 participants, and they have to make some kind of perceptual decision or something like that. They have to, we measure the time it takes for them to solve a task, and we do that, let's say, in seconds. So here we have from 0 to 4 seconds. Overall, we see that we have a mean reaction time for this task, and it's around 2.5 seconds. So the average time it takes to solve the task is 2.5 seconds around here. But crucially, we also observe that we have some participants here being very fast in solving this task, so down at something like 1 second. And then we also have some participants being quite slow, actually using 4 seconds or close to 4 seconds to solve that very same task. So basically we have a lot of variation in this data set. Now let's compare this situation to another situation. Maybe this could be a slightly different task. Again, we have participants here, 20 participants, and this is basically the time it takes to solve a task. And we see in this particular case that people are pretty consistent. There are not much variation here, so all of them solve the task in a time frame between 2 to 3 seconds. So notice also one crucial thing here, that if we take the mean, it's actually the same as up here. So we have very similar mean reaction times in this case. But if we look at the variation, it's different, and that's reflected in the standard deviation. So here we have a high standard deviation, reflecting the fact that we have a lot of variation between the data points. Down here we have a low standard deviation. And what does standard deviation really mean? So let's try and represent these data as slightly different. So before we had like the times that it would take participants to solve the task. Here we now move that down to the x-axis. So here we have 0 seconds, 1, 2, 3, 4, 5 seconds, so on and so forth. And what the way that or what this graph now represents is the number of participants, for instance, that solved this task within a time frame of 2.8 to 3.4 seconds. And here we see that 8 of the 20 participants used some time there, and we can see that from 0.5 to 1.3 we had 2 participants, and so on and so forth. So, but what we can notice here is that we have what we could call great dispersion of the data. So we have really a lot of different times represented here in the graph. So it's another way of looking at the variance. But this, the degree of dispersion of the data over this scale is really what the standard deviation here expresses. If we go down to our different sample here, or our other sample here, we see that here the values are really kind of much more concentrated on fewer bins in this. So here almost all participants are performing within 2 to 3 seconds in this task. So we have a much less dispersion of the data, and that is what is reflected by the standard deviation here. Often when we encounter these kind of summary plots in experiments, we don't see, like we do here, one bar for each participant, but we may see something like this. So here the blue bar is representing the mean, like just above 2.5. This is for this data set. And then we have what is called an error bar here. And this error bar is expressing how much variance we had in this particular sample. So here we had a high variance, and that is really what is expressed here. Similarly, the red one here represents this data set. So again, we see that the bar is showing us the mean just below 2.5 in this case. And here we have a much smaller error bar reflecting the fact that there's less variation in this particular sample, so we have only a 0.3 standard deviation here. Be aware that not all error bars reflect standard deviations. Often a graph like this would have some kind of little text, a little legend down here, or caption that would tell you if the error bars reflect standard deviation or one of the other measurements of variance, which could, for instance, be the standard error of the mean. But we won't go too much into that now. The important thing here is to recognize that in these bar plots we get some kind of measure of that express the average of a full data set, and we get some indication of how much variation there was in this data set. Now let's move on to another related issue, and that is concerns sample size. So often in experiments we are provided with these kind of information. So again from the Senju and Zebra study here, we were told that 20 participants, or in this case infants, were included in the experiment, and we get some information about their age range and that kind of thing. And why is it that it could be potentially important to know something about the sample size? Or we can just mention that like the sample size could be the number of participants. And what is also relevant in this context is, for instance, something like the number of trials or the number of measurements per condition. It could be that that in a nitrogen study like this they had only done like 1 or 2 trials, and we would then maybe worry that that what we get is not really a significant sample, and so on and so forth. So generally it can be relevant to look at the sample size. And why is that? Now let's take again an example like the one before. So we have here a number of participants. They have solved the task, and we see that there is quite some variation in the time that they have taken to solve that task. Now let's say that we only in this experiment included 5 participants rather than 20. Now that could, for instance, be those 5 here coincidentally, but it might also be that what the people that turned up for this experiment was, for instance, these 5 or these, or any combination of these people. And actually what we notice is that if we only included these 5, then probably they would not be fully representative for the full population. So if we take the mean of the performance of the first 5 here, we see that that amounts to some measurement around here. But if we take the mean of these 5, we get a totally different picture. for the exact same task. What this tells us is that to get a mean that is kind of representing the full population, which also could be much more than 20 participants, of course, probably it's not enough to only include 5 participants, because it really then becomes crucial which 5 participants is exactly included in the experiment. So what we notice is that if we have if we are investigating a phenomenon where we generally get great variance in the scores that we obtain, then 5 participants is probably not enough. Let's try, just for the fun of it, to then say that we include 10 participants. So we include these 10 and then just test if they would by coincidence be different from the other 10. And we see still that there's kind of great difference here in the mean of these 10 and these 10, which indicates to us that even like including 10 participants probably would not give us a mean that was representative for a larger population. So we really have to be careful in this particular case, because we have great variation, and we probably need at least all 20 to begin to have a mean that stabilizes and that can be thought of as reliable and representative for a population. Now let's look at the other data set that we had collected that is much less varied and much more consistent. What we notice there is that if we again take just the mean of the first 5 and the second 5 and so on and so forth, these means really don't differ a lot. And if we take like the first 10 and the latter 10, we get only very small differences here, which can tell us that in the case where we are able to collect data where people perform very consistently, we might not even need 20 participants to get a reliable mean. We can maybe do only with 10 or maybe even less. And already, because we can see that already the mean from the first 5 seem to be representing like the full sample in this case. So that's something that we can keep in mind. Let's try just to sum up some of these very basic points about these descriptive measures. So if we want to make sure that our observations can be generalized beyond that small sample that we have collected, and that they are representative maybe for a larger population, some things that we could attend to would be the variance, for instance, expressed by standard deviations of the data that we have encountered, and the sample size, that is the number of participants or the number of measurements for each participant and stuff like that. So these turns out to be crucial information if we want to assess the reliability of a particular data sample. Something that I haven't mentioned here is that sample size is often reflected in what we call the degrees of freedom. I won't go really a lot into that by now, but it's helpful to know maybe that, because you sometimes encounter that concept, the concept of degrees of freedom. But that was all for this very basic introduction to descriptive statistics.